Welcome back for another deep dive. Today we'll be looking at perfect numbers.
Perfect numbers, yeah.
You ready to get into it?
Absolutely.
Okay, so for anyone who may not know, what is a perfect number?
So a perfect number is a positive integer, meaning a whole number greater than 0
Okay,
that has this special relationship with its divisors.
so all the numbers that divide into it.
Right. All the numbers that divide evenly into it except for the number itself.
Okay,
When the sum of all of those divisors
Right.
equals the number itself, that number is a perfect number.
perfect. Okay, that makes sense. I think an example might help.
Sure.
What's a classic example of a perfect number?
The most classic example would be the number 6.
6.
The divisors of 6 are 1, 2, 3,
Yeah.
and 6.
Got it.
If you add up the divisors except for 6,
Okay.
you get 1 plus 2 plus 3, which equals 6.
Oh, okay, that makes sense.
So 6 is the perfect number.
Perfect. And we'll be using information from the Wikipedia page on perfect numbers today.
That's right. That's right.
I'm excited to get into this.
Me too. It'll be a deep dive, that's for sure.
Awesome. So where should we start?
Well, why don't we start with how mathematicians first discovered these numbers?
Okay.
We're talking ancient Greece around 300 BC. A mathematician, Euclid,
Okay.
he was one of the first to dive into perfect numbers, and he came up with a formula.
A formula.
A formula, yeah, for generating even perfect numbers.
Oh, wow. But I'm curious, like, before Euclid, did people even know about perfect numbers?
That's a great question. It's not really known if anyone before Euclid really thought about perfect numbers, but
Right.
we do know of some, like, perceptions of them.
Well, like what?
Like Nicomachus, about 100 AD, a philosopher mathematician.
Okay.
He observed some things. He correctly stated, without proof though,
Okay.
that every even perfect number follows Euclid's formula.
wow.
But he also went on to say that perfect numbers alternate ending in 6 and 8.
So like a 6, then an 8, and a 6, then an 8?
Exactly. Exactly. And while that pattern is true for the first few, it breaks down as the numbers get larger.
Ah, so he was a little bit wrong.
A little bit wrong, yeah. A little bit off. But that just goes to show that math is, always evolving.
Yeah,
Even the most brilliant minds can make mistakes.
exactly. So besides Nicomachus, were there any other, like, historical observations?
Yeah, well, there were some philosophers, Philo of Alexandria, Origen, Didymus the Blind. They talked about perfect numbers in their theological discussions.
Oh, really?
They linked 6 and 28, the perfect numbers, to
Yeah.
things like the creation of the world
Oh, right, yeah.
and the lunar cycle.
Makes sense, makes sense.
And St. Augustine also emphasized 6 as the smallest perfect number in his
Yeah.
writings about creation.
So they weren't just mathematical, they had this, like, deeper meaning.
Right.
That's cool.
It is, yeah.
So moving on in history a bit, who else made some, like, big observations?
So if we fast forward to the 12th century, we meet Ismail ibn Faliz,
The big fellas, okay.
an Islamic scholar
Yeah.
who made some big contributions to the understanding of perfect numbers.
Like, did he discover any new ones?
He did. 3 more, to be exact, which added to the growing list.
Wow.
However, he also listed some that were incorrect,
Oh, no.
which highlights the challenge of verifying these large numbers.
It must have been, like, so hard to check back then.
It was very difficult.
Wow.
Yeah, and then in the late 16th century, an Italian mathematician, Pietro Cataldi,
Cataldi. Oh,
he proved that every perfect number that's derived from Euclid's formula ends in either a 6 or an 8.
oh, wow. So he put that whole debate to rest?
He did, yeah.
Wow. So we've got Euclid's formula, but, like, how does it actually work?
So to understand Euclid's formula, we have to first understand a special type of prime number called a Mersenne prime.
Mersenne primes. Okay, remind me about those.
So a Mersenne prime is a prime number,
Love that.
and a prime number is only divisible by 1 in itself. If you take 2 to the power of any prime number and subtract 1,
Okay.
and that is a prime number,
Right.
then you've got a Mersenne prime.
Okay. That makes sense.
Yeah.
So how do those relate to perfect numbers?
So Euclid discovered that every even perfect number
Okay.
can be generated using a formula that involves these Mersenne primes.
Wow.
Yeah, it's really neat.
Okay, so how does the formula work?
Well, the formula states that
Yeah.
if you have a Mersenne prime, let's just call it m,
Okay.
then you can find a perfect number
Right.
by multiplying m by 2 to the power of, let's call it p minus 1,
T minus 1.
where p is the prime number that you use to get the Mersenne prime.
Okay.
Yeah.
So can we do an example?
Sure. Let's go back to the Mersenne prime 3.
Okay.
Remember, we got that by raising 2 to the power of 2.
Right. And then subtracting 1.
And subtracting 1, exactly.
Got it.
So in this case, p, our prime, is 2, and our Mersenne prime, m, is 3.
Okay.
If we plug those into Euclid's formula...
Okay, so we multiply 3
Right.
by 2 to the power of 2 minus 1,
Which is 1.
which is 1.
Exactly, so 2.
2, and 3 times 2 is 6.
6.
We've got our perfect number back.
Wow. So that formula works for every even perfect number.
Every even perfect number.
That's incredible.
Yeah, it's pretty amazing.
And that was proven by Euler, right?
Yes. Leonhard Euler in the 18th century,
Okay.
he proved that every even perfect number
Right.
can be expressed using a Mersenne prime.
So it has to.
It has to.
That's amazing.
It's a really powerful theorem.
Okay, so we know that Mersenne primes are kind of like essential for finding these even perfect numbers.
Absolutely.
But if we have just any prime number, does that mean we can always get a Mersenne prime?
Not necessarily. Not necessarily. Just because you have a prime number,
Yeah.
that doesn't guarantee that if you do 2 to the power of that prime and subtract 1,
Okay.
that will also be a prime. Sometimes it'll be a composite number.
Mo, can you give us an example of that? Sure. Let's take the prime number 11.
11.
2 to the power of 11 minus 1
Wait.
equals 2047.
Okay.
Now, that might look prime,
Right.
but you can divide it by 23 and 89.
So it's not.
It's not a prime. So while a Mersenne prime means we've got an even perfect number,
Right.
the opposite isn't true.
Okay.
Not every prime will give you a Mersenne prime.
Okay. That makes sense. So these Mersenne primes are pretty special.
Yeah.
But, how rare are they?
Extremely rare.
Yeah.
As of October 2024, we've only found 52.
52?
Yeah. 52 Mersenne primes, which means 52 even perfect numbers.
So they're both very rare.
Very rare. Wow. That's incredible.
And you know what else?
What?
Even perfect numbers have some cool properties.
Really?
Yeah.
Okay, I'm ready.
So even perfect numbers can be represented as the sum of consecutive positive integers.
Oh,
Like our perfect number 6.
can be expressed as 1 plus 2 plus 3,
Right.
and 28
Oh, the next one.
can be written as all the numbers from 1 to 7 added up.
1 through 7. Okay, let me check that. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. It equals 28.
It does. It does.
Wow.
And even perfect numbers can also be represented as the sum of consecutive odd cubes.
Cubes, okay.
Yeah, so 496, which is the third perfect number,
Right.
equals 1 cubed plus 3 cubed plus 5 cubed plus 7 cubed.
Wow. Okay.
Yeah, and they also have a unique representation in binary form.
Binary form, like computers.
Yes. It's always a string of ones followed by a string of zeros.
Really? So 6 in binary is just 1, 1, 0?
Exactly.
So cool.
They've got all these patterns.
What other patterns do they have?
So triangular numbers, like bowling pins?
Yeah, okay.
Well, every even perfect number we've found is also a triangular number
Really?
and a hexagonal number.
No way. How is that even possible?
Yeah, it's pretty crazy.
That's incredible.
It is. And if you calculate the digital root of any even perfect number, except for 6.
Okay, wait. What's a digital root?
So you take all the digits of a number and add them together, and you
Right.
keep doing that until you get to a single digit.
Right.
The digital root of every even perfect number except 6 is 1.
Oh, wow.
Yeah, pretty neat.
So we've talked about even perfect numbers, but what about odd perfect numbers?
That's the big question.
The big mystery.
Big mystery, yeah.
Okay, so let's get into that.
Absolutely.
We've got all these even perfect numbers with their patterns and Mersenne primes,
Right.
but now we're getting into the unknown.
That's right. The unknown world of odd perfect numbers.
Okay, let's go.
Let's do it. It's a mystery that's been around for a long time.
Yeah, have we made any progress at all?
We haven't found one yet,
Right.
but we have found a whole bunch of conditions that an odd perfect number would have to meet.
So it's like a list of rules,
Okay.
but we don't even know if it exists.
Pretty much, yeah. Like a mathematical wanted poster.
I love that. Okay, so what are some of these conditions? What do we know about these odd perfect numbers, if they exist?
Okay, so first of all,
Yeah.
if an odd perfect number exists, it's huge. Like astronomically huge.
How huge are we talking?
We're talking bigger than 10 to the power of 1500.
10 to the 1500th power.
That's a 1 followed by 1500 zeros.
Okay, so that's bigger than anything we can imagine.
Yeah, it's massive. And
Heck,
it wouldn't be divisible by 105.
Okay.
So that narrows it down a little.
A little bit, a tiny bit.
Just a smidge. It would also have to be what we call congruent to 1 modulo 12.
Okay. I don't know what that means.
Basically, when you divide it by 12,
Okay.
the remainder will always be 1.
Okay, so it has to have like a very specific form.
It does. And then we know a lot about its prime factors.
Prime factors, okay.
It would have at least 101 prime factors.
No.
Yeah, and at least 10 of those would have to be distinct, meaning different from each other.
So it's like made up of a ton of different prime numbers.
Exactly. And we even know that the largest of those prime factors would have to be greater than 10 to the 8th power.
Wow.
Yeah, it's pretty crazy. And if the number isn't divisible by 3,
Yeah.
then we're looking at least 12 distinct prime factors.
Wow.
And the smallest prime factor would have to be less than half the number of distinct prime factors it has.
Okay, so the more prime factors it has, the bigger that smallest one can be.
Exactly. It's all connected.
It's so complex.
It is. Mathematicians have also proven a lot about the exponents of these prime factors.
Exponents. Okay.
Remember when we talked about 2 to the power of something?
Right, yeah.
Well, every odd perfect number can be expressed as a product of these prime powers.
Okay.
So we know a lot about those exponents too.
So it's like a really restricted, like, recipe.
All right.
With all these conditions, do you think we'll ever find an odd perfect number?
Honestly, it's hard to say.
Yeah.
Some mathematicians think that these conditions are so restrictive that odd perfect numbers just can't exist.
So they might not even be out there.
Maybe, yeah. A mathematician, James Joseph Sylvester, said in 1888
Okay.
that finding an odd perfect number would be a little short of a miracle.
Wow.
Yeah. But even if we never find one, the search has been super important.
Right, I agree.
It's helped us learn a lot about number theory.
Exactly. It's all about the journey, right?
Exactly.
Well, we've talked a lot about even perfect numbers and all the cool properties they have.
Yeah.
And we've touched on these mysterious odd perfect numbers.
Right.
What else is there to know about perfect numbers?
Well, believe it or not, there's a whole extended family of numbers related to perfect numbers.
Oh, really? Like what?
Like abundant numbers, deficient numbers,
Okay.
amicable numbers, and even weird numbers.
Weird numbers. Okay. I'm definitely intrigued.
Abundant numbers have a sum of divisors that's greater than the number itself. Deficient numbers have a sum of divisors that's less than the number.
Got it.
And amicable numbers come in pairs.
Okay.
The sum of the proper divisors of one number equals the other number.
And the other way around.
And vice versa, yeah.
Oh, cool.
Like 2 friends exchanging gifts.
I like that analogy.
Right.
Yeah.
They always add up to the other friend's worth.
Oh, I love that. So cute.
It is.
What about those weird numbers?
Weird numbers are deficient numbers, but they have this special property with their divisors that makes them different.
Okay, that makes sense.
Yeah, it's a whole fascinating world beyond just perfect numbers.
It sounds like it. It seems like we've only, scratched the surface today.
Just a little bit.
Yeah. So let's recap what we've learned about perfect numbers.
So perfect numbers are these really cool numbers where the sum of their proper divisors equals the number itself.
We've got even perfect numbers, which are linked to those super rare Mersenne primes. And they have all these cool properties, like with their sums and their binary forms and stuff.
Exactly. And they fascinated people for centuries.
And then there are those odd perfect numbers.
The big mystery. We
Yeah.
haven't found any yet,
Right.
but we know a lot about what they would have to look like.
And that's all thanks to mathematicians who have, dedicated their lives to this stuff.
Yeah, they've done some amazing work.
That's incredible.
Right.
So what should our listener be thinking about as they go forth from this deep dive?
I think the big question is,
Yeah.
could all those patterns we've talked about, like the ones that even perfect numbers have,
Yeah.
could those be the reason why odd perfect numbers don't exist?
So, are those patterns clues to finding an odd perfect number?
Right.
Or are they, proof that they just can't happen?
It's a question that, people will probably be thinking about for a really long time.
It's so cool.
It really is. It's what makes math so amazing.
Yeah.
There's always something more to explore.
It's a journey of discovery. Well, maybe our listener will be the one to solve this mystery.
Maybe.
They could discover an odd perfect number.
Or prove that they don't exist.
Yeah, it's exciting.
Anything is possible.
So to our listeners out there, keep
Yeah.
exploring and keep those numbers crunching.
Absolutely.
Well, that's all the time we have for our deep dive into perfect numbers.
Thanks for listening.
We'll see you next time. We've been on this amazing journey,
Yeah.
exploring even perfect numbers with all their patterns and connections to Mersenne primes.
Right.
But that question of odd perfect numbers is still out there.
It's a real head scratcher. I mean, will we ever find one?
It's like searching for a mythical creature.
Yeah, exactly. We might be searching forever.
But even if we never find one,
Right.
the search itself has taught us so much.
It really has. It's pushed the boundaries of number theory, that's for sure.
So as we wrap up this deep dive,
Yeah.
what's the one thing our listeners should be thinking about?
That's a good question. I think one of the most interesting things to consider is this. Could the patterns we see in even perfect numbers,
Right.
those unique sums, the binary representations, the connections to geometry,
Yeah.
could those be the reason why odd perfect numbers just can't exist?
So are those patterns a guide to finding an odd perfect number?
Right.
Or are they like a big road closed sign?
It's a question that's going to keep mathematicians busy for a long time.
Yeah, maybe centuries.
Maybe, yeah. But that's what's so cool about math.
It's true.
It's a never-ending puzzle.
Always more to discover.
Exactly. And who knows, maybe our listener will be the one to crack the code.
Oh, yeah.
Maybe they'll find that odd perfect number, or maybe they'll prove that they're impossible.
That would be amazing.
It would. So, to our listeners out there, keep exploring, keep that curiosity alive.
Yeah, keep asking those what-if questions.
You never know what you might find.
That's right. Well, that brings us to the end of our deep dive into the world of perfect numbers.
It's been a fun one.
It has. Thanks for joining us, and we'll see you next time.